Moin, this is KANLab, an interactive playground for you to experiment with Kolmogorov-Arnold networks. It is a fork of the popular TensorFlow playground, which lets you experiment with multi-layer perceptrons. Since Kolmogorov-Arnold networks are a promising alternative to multi-layer perceptrons, we aim to create a KAN-based alternative to the TensorFlow playground. But what does it do? On the right side, you see the output of the network, together with the data points used for training. The task of the network is to color the background in such a way that the blue points get a blue background and the orange points get an orange background. With that said, let's train our first KAN. Nice, it worked! But a lot of things happened at the same time. Let's go back and look at the important parts. In addition to the output, we also have a hidden layer and the data input. In between these are univariate activation functions implemented as B-splines. We reduce the learning rate to have more time for inspecting the development of the activation functions. Hovering over one shows a bigger version with more details. Among these are histograms of the activations, one for the incoming activations and one for the outgoing activations. The incoming and outgoing activation variance is also visualized by the thickness of the lines left and right from the activation function. We notice that not each pathway shows a high activation variance, indicating that certain pathways are more important than others. If we now deactivate the activation flow by, let's say, manual pruning, we can force the network to find a new solution. Next, we are going to have a look at spline manipulations, but we need a smaller network for that. Again, we hover over an activation function with our focus on the green line and the orange dots. The dots are the learnable control points of the B-spline and they determine its form. We see that the network found a solution. Observe the output while I manipulate the control points. If my shenanigans get too extreme, the network can also get stuck in a local minimum, visualized by the blue X on the output. But eventually, we are nice and help the network to get out of it again. The circle data set is a nonlinear task, but it's getting too easy. Let's go for the much harder double spiral data set. The network found an interesting solution to say the least, but the test loss of 0.23 is still quite high. We might be able to get a lower loss by increasing the amount of learnable parameters. Just like for multi-layer perceptrons, we can do this by creating deeper and wider networks. But for KANs, you can additionally increase the number of control points per spline. At its lowest point, the test loss decreased to 0.026, which means that we successfully got it around 8 times smaller than before. One of my favorite examples is to play around with a spline degree of 1. You really see the low degree in action because of these straight decision boundaries. This is not only true for the output, but also for the intermediate decision boundaries at the nodes. A spline degree of 1 basically means linear interpolation between the control points. There's a lot to discover and much more to learn. Have fun experimenting on KANLab.app.